Welcome back to the deep dive. Today, we're taking a closer look at just one entry from the Online Encyclopedia of Integer Sequences, the OEIS. We're focusing on A000338. Now, for you, our number theory student listeners, our goal is really to peel back the layers here. Its formal name is, well, it's a bit of a mouthful. Expansion of by 3, 52x, 1 by 3, 1 by 4. Sounds complicated, maybe, but we promise there's some elegant math hiding in there. So, the sequence starts out like this. 5, 18, 42, 75, 117. What makes just a string of numbers like that so rich mathematically?
That's a great question. It really gets to the heart of the OEIS, doesn't it? Even a short list of numbers, derived from an algebraic expression that looks kind of complex, can actually open doors to some really deep connections in mathematics. And this one, A000338, it's tagged with meaning non-negative terms and also easy, which in OEIS terms suggests its definition is relatively straightforward to get your head around, makes it a perfect starting point, really.
Okay, so let's dive into that generating function you mentioned. For our listeners, what does expansion actually mean in this context? How does that big formula by 3, 5, 2x, 1 by 3, 1 by 4, how does it make those numbers? 5, 18, 42.
Right. So that expression, that's the generating function. Think of it like this. When you expand it out into an infinite power series, something like C0 plus C1x plus C2 by 2 and so on, the numbers multiplying each power of x, those coefficients Cn, those are the terms of the sequence An. It's basically a compact algebraic blueprint for the entire sequence. And what's quite insightful is a form Simon Plouffe used back in 92. He wrote it as 1 plus x plus by 2, 5, 2x by 3, 1 by 3. See how that breaks down the 1 by 3 part? It shows you the factors 1x and 1 plus x plus by 2. That often gives you clues about the underlying structure, like its recurrence.
Oh, I see. So that structure is kind of embedded in the different ways you can write the function. And speaking of structure, the entry mentions an offset 3, 1. What does that tell us?
Yeah, that's a key piece of information. Offset 3, 1 means the first term listed, the 5, that actually corresponds to A3 in the sequence, not A of a 1.
Oh, okay.
Right,
Yeah.
so the coefficients for x0 by 1 by 2 in that power series expansion would actually be 0. A3 is the first non-zero term we care about here, the 1 part of 3, 1. That usually relates to the index from which the recurrence relation holds, so from n1 onwards for related calculations.
Got it. That makes sense. So we know how the numbers come about, but who first put this sequence, on the map?
Well, this one goes right back to the founder himself, N.J.A. Sloan. He originally authored this entry. It was even in his big 1973 book, A Handbook of Integer Sequences.
Whoa, okay. Foundational stuff.
Exactly. It's a core entry, and it's still relevant. Looks like it was last updated September 14, 2025, quite recently.
So we've got the generating function, the offset, the history, but is there a simpler way, like a step-by-step rule to get the next number without doing that whole expansion thing every time?
Oh, absolutely. There's a much more direct way. A000338 follows a clear linear recurrence relation with constant coefficients.
Okay.
Its signature in the OEIS is listed as 3, negative 3, 1. What that means is each term an can be calculated from the 3 before it. The rule is an equals 3an1, 3n-2 plus an3.
Ah, much simpler.
Yeah, once you have the first few terms like 5, 18, 42, you can just use this rule to generate all the rest. Much easier computationally.
Okay, now this is where I think it gets really interesting. Beyond the formulas and recurrence, does this sequence actually count something? Like, is there combinatorial meaning, something tangible?
Yes, it does. And you're right, this is often the most exciting part. The key reference points to J. Riordan's 1954 paper on discordant permutations.
Discordant permutations.
Exactly. This sequence, A000338, is fundamentally tied to counting these specific kinds of arrangements. Imagine you're arranging items, but there are rules about where things cannot go. It's a bit like derangements where nothing ends up in its original spot, but more general. It counts arrangements where elements avoid certain forbidden positions, not just their original one. So it gives these numbers a really concrete combinatorial significance.
That's fascinating. What a journey for just one OEIS entry, A000338. We went from that complicated-looking fraction, uncovered the numbers it generates, its history with Sloan, found that neat recurrence relation, and landed on this cool connection to counting discordant permutations.
It really illustrates the power of the OEIS, doesn't it?
Yeah.
And it makes you think, how many other sequences are sitting there looking abstract, just waiting for someone, maybe even you listening, to find their hidden combinatorial story?
Exactly. A great thought to end on. Keep exploring, keep asking questions, and join us next time for another deep dive.